Good afternoon. I'm happy to be here and present our work titled Diffusion versus Autoregression Models. This work is the collaboration between myself, Vladimir Zorigin, and Valentin Malik. We started to doing it during the School Tech for Being Smiles summer school. And first of all, I would like to express my gratitude to the program committee of ICCQ 2025. We were happy to receive detailed and helpful comments from the reviewers that significantly improve this paper. So thanks for the reviewers for their contribution. Today I'll talk about investigation into whether diffusion-based language models and how they can outperform traditional autoregressive models in a specific domain of code comments translation. Um, let's start with the problem we're trying to solve. So in modern software engineering, global development teams often face language barriers in code comments hindering collaboration. Effective translation is crucial for cross-team understanding and automated documentation. And while we look on diffusion-based LLMs for this work, um, uh, when the dominant paradigm for today's autoregressive decoding, DLMs with diffusion-based LLMs perform intelligently denoising over entire sequences. So our goal was to see if these theoretical advantages translate into practical tool for developers. Um, uh, to understand our experiments and results, we must first clarify the fundamental difference between these two types of architectures. Um, Autoregressive models generate text token by token from left to right. Um, Critically, each new token is predicted based only on the previous ones. This can limit global coherence because decisions are made locally. Once a mistake is made earlier in sentence, it's propagate. But in diffusion LLMs, we start with the fully noisy sequence and iteratively denoise it. They refine the entire sequence in parallel of over multiple steps. As you can see on the right diagram, the model can see the end of the sequence while generation the beginning. This parallel iterative refinement allows the global planning. The model consider the entire output potential of each step, which leads to the better structure consistency. I think it is a key requirement for technical code comments. Um, Diffusion-based LLM is uh, built on diffusion framework as models for images. It have two main processes. Forward process that um, inject noise and reverse process to remove it. During pre-training, this type of models work with corrupt sentences. Tokens are randomly masked, and the model, which does not see the original text, must predict it. Next, supervise fine-tuning step um, is typical for language models, and here we masking is applied um, selectively to the response part, while the prompt remains visible for the model. This ensure the model learns to generate answer conditioned on the context, on the questions, on the task. So finally, during the inference, the model work with a fully masked noise and internally predict token, the mask some of them, and predicts the key until the sequence is clean. Um, because the process is uh, iterative, there are several key parameters that influence both quality of generation and speed. Um, we focus our study on these parameters, and we can mention the four main of them. Number of step is naturally for us, the more steps we have allow to refinement for the model, the higher quality we have, but the time of generation linearly increase with it. The second is noise schedulers, which define mathematical rules. So how we add the noise on the sequence. The third is the masking algorithm. At each step of the model predict token, but we don't keep all of them. This algorithm decides which token are reliable enough and keep them and which should be remasked again. Finally, token per step generation ratio. This refines to ratio of generation text length to the number of steps. This parameter directly control the trade-off between how short the model is and how fast it runs. Um, our experimental setup was built on the dataset, this corpus of code and with comments. The task was translation in code comments from Chinese into the target languages. We use English and Russian. We intentionally choose the English or Chinese as a source because it is a high resource language in code repository, but structurally very different from English and Russian. For metric, we use BLEO and Comet. BLEO for lectural fidelity and Comet for semantic adequacy. Comet particularly more important here because it correlates better with human judgment. Um, we also choose the large amount of fluid models, diffusion weights, base, including variance of Dream, Diffusion, and LADA, and compare it with the after-regressive baseline. It was Quen 2.5 model. We select this model because it matches the parameter size and some of the fusion-based models was based on Quen as well. Here, I think the main our result we have mm, bold numbers indicate the best performance of Dream Instruct achieve that can achieve strongest overall performance. Uh, we attitude to the success of Dream Instruct to bidirectional processing capabilities of diffusion models. So Dream can utilize the context um, from the entire code snippet simultaneously when uh, translating the specific theorem. So uh, here we can have example of translation, example of code snippet, um, and we can see the calculate recall rate is it was a ground truth translation, while the autoregression models output only calculate and missing um, some technical term of recall rate. Um, Here, diffusion model do the best translation. Um, Earlier, I mentioned the token per step generation ratio. We consider an experiment to see how the parameter affect performance using Dream model, our the best from the previous experiment. Um, the data clearly indicates a peak of performance when the ratio is exactly one, meaning that one token generate um, there are one denoising step. Um, as we increase the ratio, we try to generate two or four or eight tokens per step, the quality degrades significantly. This is the main trade-off current diffusion models face to get the best quality, and they need more time, more steps of the noising process. Also, we have several masking algorithms. Um, Remember, at each step, the model predict token, and we need to decide which one to keep and which we need to regenerate. Our focus on four main strategies. Origin was used in the baseline. It is a default selection, random selection strategy. Mask GT plus is the algorithm. We try to unmask the token that are more informative in some kind of um, top K margin. The strategy ties the token based on prediction confidence that model give us with the tokens. And entropy approach, uh, it target token with high entropy for masking, focusing the model on difficult part of sequence to generate it with the good confidence and low entropy. So here, the result of trying this algorithm, according to result, I think I understand that algorithms is matter. And as you can see, all probability-based methods consistently outperform the random baseline across every metric and every language. This leads us to the important conclusion. More intelligently selection token algorithm based um, on the model confidence or assertively, it is very crucial. Um, it directs the denoising process to uh, most informative position result in the better final outputs that simply uh, picking random tokens. Um, to summarize our work, I will give three main points. The first, it's, I guess, the main finding that the diffusion-based LLM demonstrate superior translation quality compared to sales-meshed autoregression baselines in the task of code comment translation. Um, but the second point with the high quality comes a cost. We find that the DLMs require a low token per step ratio to achieve the peak of performance on this translation task, especially. This means the mm, Um, currently, models require more generation step, which leads us to higher latency than aggressive models. Uh, for the future work, we uh, will focus on optimization of this process and investigate advanced sampling techniques, adaptation of the models with fine-tuning or reinforcement learning uh, with the special data sets um, and scaling of our experiments to the more uh, reliable data. So I think so. Thank you very much for your attention.
Thank you for your work. It sounds interesting. Um, I wonder why don't you, or maybe you do, why don't you try to use the code itself on top of the comment that you translate in order to get better context? Or maybe you tried that.
Yeah, we tried to add the code
Mhm.
to translate it in context.
Uh-huh. Oh, I just missed that. Okay.
Okay.
And how much code do you put there?
We have not so big data set here. Um, we interesting to try some hypotheses, and we take 300 sub samples of it with short code snippets uh, that we can put in context to the one request for the model.
But can you go to the next slide?
Okay.
No, next one. Further. Yeah, look here. It seems that you only take the comment from this example on the left, only the Chinese comment, and then you send it to the model and you get back the answer. But you don't send the Python code to the model. You only send the text. Am I right?
Uh, not a bit. We send the code as well to the model.
So how much code in this particular example? How much
Uh,
Python code go there?
Approximately, it is a part half of code that we have for this example is shown on the slide.
So like 2 lines, probe.
No. Well, good. Here we have them. That 10 lines.
So all 10 lines, they go there to
Yeah.
the model.
To the prompt for the model when we ask to translate.
Uh-huh. And then you ask the model to translate only one particular line, which is at the bottom.
Yeah.
And do you ask specifically the model to please translate line number 5?
Some kind of, yeah.
So what I'm just interested how the prompt looks like.
Yeah, we do some prompt engineering investigation here and get some kind of task to translate. Here you have the context of the comment, a comment. Model will output on the
okay, you
translation.
you submit it separately. Okay, you just say, please translate this, and here's your context.
Yes, yeah.
Okay, makes sense. Interesting. I just wonder what's going to be the effect of the changing the size of the code that you provide. If you provide just a few lines, that's going to be one story. But if you provide 100 lines, which goes around, which stay around this particular comment line, that maybe the accuracy will be higher.
Yeah,
maybe.
it's interesting. We can test it in the future work.
But maybe slower. Okay, and you also put it online so we can play with that? Is it somewhere hosted publicly? Your product?
At this time, we don't host it publicly. We just started our work with experimenting experiments with diffusion LLMs and find the cases, the tasks where it can be more accurate, more interesting than autoregressive approach. This was the one of these tasks.
And did you try to make some conclusion in the direction of applicability of your results to something maybe not directly related to comments translation? Because you found out that diffusion models, they're more effective for this particular kind of task. And maybe that can be, extrapolated to some other areas of science, of computer science. You can say maybe this is true also for variable renaming, for example. That's another task, which is also suitable for machine learning, for artificial intelligence.
Yeah, I think. Yeah, thank you. I think diffusion LLMs can be good for NER task, for some kind of anonymizing documents, searching names, phones, and so on, and mask it before you send data to external server. I think it's some kind of similar task, but here we have the perspective of DLMs as well.
But then the next question is whether this conclusion is novel. Are you the first one in the world who are saying that the diffusional model are more effective than the faster version? So I suspect that this is not your discovery. It was known before, I guess.
Maybe I don't know all resource for diffusion LLMs, but it is a new idea. The many of papers was published only for 2025 year. Yeah.
Okay. But in any case, even if this idea was published earlier, your contribution is valuable to the same idea. Your result and your study confirms what was maybe already said before, which is good. That's what I'm saying. because you study only specific problem, only one problem of translating comments from one language to another, but you found out that diffusional LLMs are effective. That may be helpful to other researchers in the future to also look at them, because they know your results. They may say, okay, we're going to also use the same, but for a different problem. So,
yeah, I think so.
That's great. Okay, thank you very much. Appreciate it that you came to our conference with your study results. And I wish you good luck in your next steps.